area between curves. Now that we have a good understanding of how the area works in relationship to the x-axis, we want to now use the information we know to talk about how we might find the area between two functions. So consider the picture below. Our top function, we're going to call f of x. We're going to talk about that first. So f of x is the red line. And what we know from before is that if we wanted to consider the area under the curve of f of x, we could take the integral between the bounds we were interested in. So for this example, let's consider the area from 0 to 4 of f of x dx. So the area under the curve from 0 to 4 is going to be all the area between the red curve and the x-axis by definition. We can see that that area is positive, and we can see it's bounded by the x-axis. Let's call the second function, the blue function, g of x. If we were to take the area under the curve of g of x from 0 to 4, we would have the area bounded by the blue curve and the x-axis. So all this area here. So if we're interested in the area between curves, then I'm going to suppose here, if we're interested in the area between curves, then I can see here that if I were to take the red area, the area under f of x, and subtract off the blue area, the area under g of x, what remains is the area between the curves. So I want to do, again, the area under f of x minus the area under g of x, and that will leave me with the area between the curves. Because I'm looking at both of these from 0 to 4, one set of bounds, I can write this in one integral. So the integral from 0 to 4 of f of x minus g of x dx will give me the area between these two curves, right? This area here. So we can generalize this, right? It's going to be the integral from a to b of f of x minus g of x dx. And the reason why this is not as intuitive is because there was no reason that the top function had to be f and the bottom function had to be g. And if we were to have switched our labels, we would need to switch our formula. So instead, it's easier to think about it as top function minus bottom function. Most of the time, you won't even have f of x and g of x. You'll have functions in terms of y equals. So you're going to need to remember that you always want to do the top function minus the bottom function. So let's see how this works. Example 1. Find the area between y equals x plus 5 and y equals 2x plus 1 from x equals 0 and x equals 2. So the bounds are important so that we know where we're looking. So that means I can shade in on my picture here the area that I'm trying to find. So it's this area here between these two curves. So what I need in order to be able to do this is I need bounds, and I need functions, and I need to determine which function is on top and which function is on bottom. So here, the bounds are given to me within the problem. I'm looking between x equals 0 and x equals 2. Remember, the numbers that go on the bounds of a definite integral are defined by independent values. So here, we're looking between 0 and 2. Now, I need to do top curve minus bottom curve. Here, I've labeled them in the corner. But if you weren't sure which one was on top and which one was on the bottom, you'd want to graph them on your calculator yourself so you could determine which one was on top or bottom. Another way to do this is you could plug in a number between 0 and 2 to determine which one was on top and bottom, because the higher y value function will be the one that's on top. Here, my x plus 5 is on top. So I have x plus 5 minus, now the term on the bottom is 2x plus 1. I need to use parentheses because there's more than one term. So my integral looks like this. You can enter it just like this into your calculator, or you can simplify it first. Either way, you should get the same answer. So if I simplify, I have an x and a minus 2x. So that's a minus 1x. And then I have a 5 minus 1, which is going to give me 4. So the simplified version, if you'd prefer to use that, is negative x plus 4. However, as I mentioned, you can leave it in the first form because your calculator knows how to crunch those numbers as well. Just be sure that you are using parentheses the same way I did so that you don't lose any of the terms with that minus sign. So when we put all those numbers into our calculator, we're going to get 6. So either version of that into your calculator should give you 6. The area between the two curves has an area and space of 6 units. And we are able to find that by doing top curve minus bottom curve. If you had flipped these and done bottom curve minus top curve, what you would find is that your area would have been negative 6. So keep that in mind. Let's look at another. Example 2. Find the area between y equals 3x and y equals x squared from x equals negative 2 until x equals 1. So here, I'm going to shade in the area that we're interested in. We're interested in the area right here between the curves all the way until here. So you may be noticing that something really interesting happens, and we have to be very careful about how we handle it. So our formula says that to get the area between curves, we need to do the top curve minus the bottom curve. But in this situation, the curve that's on top changes at x equals 0. So that means we can't just set up one integral to find this area. Instead, we have to set up an integral for each of the areas that has a different curve on top. So that means that my first integral, as if I go from left to right, is going to go from negative 2 until 0, because that's where I'm going to change. And from negative 2 until 0, the red curve is on top. The red curve is my x squared minus the bottom curve, 3x dx. When I plug that into my calculator, and I'm very careful about it, I'm going to get 8.667. So that's rounded to 3 decimal places. Now, at 0, it switches which curve is on top. So I have to set up a separate integral to represent what's happening from 0 to 1. So from 0 to 1, I'm going to have 3x minus x squared dx. So again, because I changed which curve was on top, I had to set up a separate integral to do that. So here, if I plug that into my calculator, I'm going to get 1.167. 1.167. So I now need to take these two areas and I need to add them together. So 8.667 plus 1.167. If I add those up, 9.834 approximately. So I have to be really careful here. And one of the reasons I have to be especially careful is because if I didn't have my graph, I might not have known that these functions switched which one was on top. So it's always a good idea to graph these if you can. Otherwise, you may not have a sense of which function is on top the entire time. Let's look at another example. Example 3. Find the area naturally bounded between y equals 3x and y equals x squared. So we're working with the same two functions we looked at in the previous problem, only now I'm not given explicit bounds on where to look. Instead, I'm told that I'm looking for the area that's naturally bounded. So I have to graph this two functions here to understand where I'm looking. So naturally bounded means that I'm naturally enclosed. So that happens in this little area here. That's the area I want. All the other areas on this graph would go on forever and ever, and I'm looking for the part that's bounded. So that means that in order to find my points for integration, I need to figure out where these two functions intersect, because that's going to be the points or the x values that I'm going to need to use for my integral. So I can look at the picture and have a pretty good guess, but if I want to do this explicitly, I can set my two functions equal to each other. So that's a good first step here. if I set 3x equal to x squared, solving that will tell me where these intersect. So I'm going to subtract the 3x over, and I have 0 equals x squared minus 3x. I'm going to factor out an x, and I have x times x minus 3. So that tells me that x is 0 or x is 3. So I can look at the graph and I can see 0, and I can see this happens at 3. So that would have likely been my guess, or I may have had some algebraic intuition. But again, if you want to know exactly where two functions intersect, you can always set them equal to each other. So now I know that my bounds of integration are going to be from 0 to 3. And again, I need to do top curve minus bottom curve. So my top curve here is the line, which is 3x, minus the bottom curve, which is x squared. So the integral that I'm taking here is the definite integral from 0 to 3 of 3x minus x squared. When I plug that all into my calculator, I get 4.5. So that enclosed area there is 4.5. So again, if you're not given bounds in your problem, that means there's a natural set of bounds that happen to enclose the area. And to find them, you need to consider where your functions intersect. So let's look at a word problem to see why we might be really interested in the area between two curves. Example 4. Suppose that the rate of oil production for a country can be modeled by Q of t equals negative 4t squared plus 35t plus 500 million barrels per year, where time t is in years since 2000. From 2000 to 2009, this country exported oil to the United States at a rate of R of t equals negative 2.5 t squared plus 20t plus 250 million barrels per year. Part A. Graph both oil production and oil exportation on the same graph. So you want to be able to get both of these graphs on your calculator to see what they're going to look like. I want you to notice the scale on the x and the y that I've used so you can set your calculator window to the same thing so that you can see these same functions. I'm going to label these, and I know that my Q of t should cross through the y-axis at 500 because when time equals 0, my Q value, or my dependent value, is 500 from this constant, the intercept. So this top function is my Q of t, and the bottom function is my R of t. So again, the top function is going to be how much I produce, and my bottom function is how much I export. Let's do some other analysis here. If the rate of production and the rate of exportation continue at the same rate, do you expect demand of exportation to exceed production? If so, when? So we want to know when the amount of oil that we're exporting is going to be more than what we're producing. So if we look at these rates, right, we can see that right around here, the rate at which we are exporting is exactly equal to the rate at which we are producing. So if we move past that point, then all of a sudden the rate at which we are exporting is higher than our production. So this happens at roughly, I would say 18. So I would say around t is approximately 18 is when the demand for exportation is going to exceed our production. Remember, time was in years since 2000. So that means that this is going to happen in the year 2018 if these rates continue. Part C. Find the area between Q of t and R of t from 2001 to 2009. What does this represent? So that means that we need to do the area between curves. Our bounds of integration, remember, time is in years since the year 2000. So from 2001 to 2009 is going to be an integral from 1 to 9. And then we're going to have to do our Q of t equation minus our R of t equation. So that's going to look like this. So we're going to have our top function, which we said was Q of t, minus our bottom function, which is R of t, from time equals 1 to time equals 9 dt. So when we plug this all into our calculator, we're going to have to use a lot of parentheses. Make sure especially that you have parentheses around this second term because of this minus. That minus has to go to every single term. So when we plug this all in, we get 2,236. But we have to remember what this represents. So if we're integrating the rate, let's go back up and look at what the units of our rates were. So notice that the rates were in millions of barrels per year. And then we integrated over years, which means that when you integrate either one of these functions or both of them together, your units are going to be million barrels. So here, if we talk about the area between the curves, what we're looking at is how much was produced from 2001 to 2009. So that's Q of T minus how much was exported. So what's left is what we found. So that's how much the country had left over after it exported some units to the United States. So here, 2,236 million barrels. And that's how much the country had left after it exported some to the United States. That's how much they had in their reserves. So that's the meaning of that number in this context.